Okay, Assalamualaikum and good morning, everyone. So I hope you had a good first test yesterday. Was it yesterday or the day before? Uh, so I'll try to get that mark soon. Uh, so let's just recall what we have done in the week before. I believe in lecture 5, which I've already uploaded on the Putra Blast together with lecture 6. Okay, essentially the last thing we did was to give you a general formula for the determinant single line rather than involving a lot of different ideas about cofactors and things like that. But now one is actually using this works. Okay, one is using what we call the alternating tensor. Okay. Note that this is not quite inside your Boas book, but I simply include it in so that you get to know, you get to be familiar with some of these ideas, and they are mostly used when you do calculations with general statements. If you have your matrices given to you with numerical numbers inside it, then you probably do it just the old way of doing it. Okay, if you have a thing to prove in general without having to know what the numbers inside your matrices are, then these kind of formulas are important. So I'm just teaching you as an for you to know, okay? Because you need to know a little bit of the reasoning behind these theories, and they are often taught in courses of mathematics on matrix theory or some advanced linear algebra. Okay, so today we're going to leave that. Okay, again, it depends on you whether you want to use this or not. No, I leave it up to you. Okay, but I'm pretty sure if you have done some advanced calculation, you might need some of these kind of things. Okay, so today we're going to look at a new lecture in the notes. So we are still what you call touching upon matrices, and in particular we are still using matrices to help you solve linear equations. So let me just remind you what Cramer's rule is. I think I've somehow mentioned this to you before. So you have done Cramer's rule, at least for the case of two simultaneous linear equations in this way. And if you simply just use the technique of elimination, okay, so you use elimination of variables, one can arrive at this particular solution for x and y. Your x and y are the variables, okay, remember that. And the rest over here, even though these are done in a much more general way, because we want to see the theory behind it, okay, usually there will be numbers here, and then you'll be able to plug in those numbers over here and essentially solve for x and y, okay. But one of the things that you probably now will be able to see is the fact that if I write the coefficients over here as the matrix M, so what are the coefficients here? A1, B1, A2, B2, okay? And this equation becomes M times xy equals to C1, C2. And you'll be able to see that the thing underneath, the denominator over here, that gives you the solution, essentially is the determinant of M. So you have A1, B2 minus A2, B1. Okay? for both the solution for x and y, but the one on top is involving your c's. But if you were to write in a way that you just replace, for example, for the case of x, you take the first column here and replace it by c1, c2, okay? Then essentially the numerator that you have over here is just given by the determinant of that matrix by replacing the first column over here. By the way, are you seeing the cursor moving? Please let me know. Can you see my cursor actually moving at this point? Oh, you didn't see. Okay. So in other words, okay, what we did was to take this as a column here, okay, and replace it by that. You can see me scribbling, right? Okay. So in other words, what happens over there, if you look at the numerator here, okay, they are just the determinant of this matrix, okay? And similarly, if you look at this one, okay, is replacing your b1, b2 here and keeping a1, a2, okay, by c1 and c2, and essentially you have that matrix. And if you take the determinant of that, you get your a1 c2 minus a2 c1. So in other words, your solutions are now expressible in terms of determinants, okay? But the one on top is essentially your matrix M, but being replaced by your matrix M over here, being replaced, the columns replaced by this constant C1 and C2, okay? Now, okay, this looks fine. So what? You may say, then can we generalize this? That's essentially the main idea here. You can actually generalize this, and it's essentially just again the same Cramer's rule. So you have the n by n case. So in other words, over here is solving n simultaneous linear equation. Okay, for which you rephrase it in terms of this matrix multiplication. So you have this coefficients multiplying the variables over here. So here's the coefficients multiplying the variables, okay, and then giving you these numbers for each of the rows. Okay, row 1 here, row 2 here. So the one row 1 multiplying the variables give you the C1 over here, row 2 multiplying the variables will give you C2 over here, and so on and so forth. Okay, so you can generalize this idea of Cramer's rule because now you're able to write this in terms of matrices. One can replace that. Okay, I can now find the solutions in terms of determinant in this way. And remember, it's not just two variables, you can do it for the n variables. How do you do this? For the first variable, you just replace your matrix M, the first column, by your right hand side. Okay, so this is from your write this over here. This is your right hand side. So you replace the first column of the matrix M by your right hand side of your equation, and that gives us the solution to x1. For the second variable, so this is second variable, x2. Let me just check if everyone is able to come in. Great. So for the case of the second variable, then you replace the matrix M, the second column matrix by the right hand side. Okay. And if you go for the third variable, then you use the third column and replace them. Okay. So you can do this, and essentially all you need to have in this particular case to solve the simultaneous linear equations is to know how to calculate determinants. Okay. Now again, why is this possible? This is a bit of a theory behind it. Again, you are not required to know this for exams or for tests, okay? But as a undergraduate student at this level, you need to know why something works, okay? Because you are already you have that mental capability to actually understand things, right? So why it works essentially is from the properties of determinants. Oops. Very good at underlining things. So what happens over here, you know how to calculate determinants for n by n matrix, and you remember that if you multiply, say, if you multiply the first row or the first column or one individual row or one individual column by a number, that new matrix will have the determinant by that number times the determinant of the original matrix. So you can check back the properties of determinant before this. And then the other thing that one can also do, so here is just multiplying it with x1 over here for the first column. Now what I can try to do is, okay, I can do this trick from the row reduction technique, okay, by adding what you call adding the other columns. Should I say other columns or? Yeah, adding the other columns. In this particular case, let me just check. Yeah, so you add the other columns, so that in other words, this is no longer just x1 and x1 only, but you have all the other variables, x2 and x3 and so on. What happens over here, you can actually do this and still retain the same value, is because if you remember, when you do determinant, for example, let's say do the 2 by 2 case, for example, A, B, C, D, you can check this for yourself. If I simply, let me try to make sure that I do the right thing here. This would be equals with 1, so I should have I need an addition of C and D. So that means I do this, and that determinant should be the same. Please check, okay? Why? Because it's essentially those thing addition is going to be the same as that particular row. So when you have okay, maybe I'll go here. When you have for example A B, for example, you know that it's going to be equals to determinant equals 0. So the addition of a particular row to the first row, for example, will not affect the original determinant, okay, because essentially you are just adding 0 here. Okay, so you have that to be now equals to x1m. Okay, and then you also know that you have this equation. Okay, so I can now look at all of this, okay, and see what they are. I hope you can, because you cannot see my cursor, so you can consider all this thing, all this equation over here of the first column. They correspond to this equation over here, for which you can actually replace it by your C's. Okay, so in other words, this thing here is still equals to the same thing over there. And this is for the case of multiplying by x1 to the first column, remember. Okay, so I can do the same for the other columns if I want to. Okay, so in general, I can have the I variable xi multiplying your what you call multiplying the like before. Let me go back, multiplying like this over here. Okay, so instead of the first column, now we'll have the I column. Okay, and then redo all the same steps, and you'll be able to write in terms of this. What is m1? What is mi? M1 is the one replacing your first column by the right hand side. Okay, so this is m1. So if mi, then you replace the column of the ith column of m by c's, and then take the determinant. So essentially now that tells us, okay, these are just your generalization of your Cramer's rule for the case of two simultaneous linear equations. Okay, again, these are just theory. I will not basically ask you on the theory itself, but it helps you understand better why this technique actually works. Okay, so now let's consider an example here. So here are set of three linear equations over here. I can rewrite this in terms of a matrix equation. So these are just your coefficients. Okay, these are coefficients from here. These are coefficients coming from the second one. Okay, and the third one, last one. Okay, and then your right hand side are now written as two. Here, your right hand side here are now written as a column matrix over here. Okay, so given that set of linear equations, write in terms of a matrix equation, and then try to solve it using Cramer's rule. Now there is an assumption that that the equations that you have is in a way has a solution. Okay, that assumption has to be there, meaning if you have the cases where your simultaneous linear equations are not really having any solution, then this doesn't work at all. Okay, so here we assume that the set of linear equation has been checked in a way that it has a unique solution. So you calculate the determinants. So in this case, I calculate, for example, the determinant of m first. So this is m, and you just carry out the calculation. Please check again. I might be getting wrong answers usually. Well, not usually, meaning it happens at times. I get wrong answers, but you can check that this is actually 49. And then for the matrix M here, replaced by the first column by that, okay, then you see that this is M1. You can see that this is now replaced by that, okay. and check again what is the determinant of this new matrix. Then it gives you minus 49, and then check again this column. This column is now replaced by that. That gives you M2, and finally for the third column, okay, you can see 2, 2, 1, 2, 1, negative 5, 2, 1, negative 5, 2, 1, negative 5. Okay, and you do all the determinants. Again, then you'll be able to solve using Cramer's rule to get the solution for x1, x2, and x3. Okay, again, please check this for me. So one could do this for a bigger matrix. The only thing about this technique, determinants are in a way we call, they are not a linear kind of process. No, there are a lot of different different things are involved inside this determinant process. But if you can actually program this, then you can be able to solve simultaneous and linear equations easily using determinants. Normally, in most of the cases, you probably see programs being written down using row reduction techniques. That would actually, in a way, it's easier to implement inside computer programs. Okay. Let's go to a different topic, which is again related to the matrices and also determinants, which is the idea of an inverse. What is the idea of an inverse? No, these are just generalization of a reciprocal for numbers. When you multiply, say, multiply a with reciprocal of a, that gives you 1. Okay, so these are numbers. So instead of numbers, you are replaced by an array of numbers. Replaced by array of numbers, which now becomes a matrix. What will be the analog of this equation? Well, the analog of this equation is essentially to say that there is such a number or there is such an object which is called the inverse of that object. Okay, so the inverse of that object, for example, is usually given by m with superscript -1, and that doesn't mean it's taking the matrix with the power of -1. That is just a symbol. Okay, please don't get confused with this idea, but this is just a symbol saying that, okay, that is essentially what we call the multiplicative inverse of your matrix M. It doesn't mean your M taken to the power of -1. Okay. So okay. So the what replaces the 1 over here? The 1 over here will be replaced by the identity matrix. And what is the identity matrix? Essentially, was a 3 by 3 case. It will be just that. It will be 1 along the diagonals and 0 elsewhere. Okay. So you multiply the inverse with, to the matrix M, you'll get the identity matrix. This is multiplying by on the left, okay? Getting confused with left and right now. Multiplying M inverse on the left, but you can also do the same multiplying M inverse to the right, okay? And that gives you essentially the identity matrix. An identity matrix, of course, you know, it's quite easy to see that you apply identity matrix at multiply it with on the left or right, it will just give you back the same matrix. So in order for M to have an inverse, one of the things that we shall see later on you need your determinant of M to be non-zero. Okay, but there are cases where you have a matrix M and then you have your determinant of M equals 0. So in that particular case, we call that matrix M to be singular. Usually this imply this for the case of the determinant M equals 0. If your determinant M is not equal to 0, then we say that matrix M is invertible, and you can actually find your inverse matrix. Okay. Again, these are just things, just recalling what you have already known for the case of 2 by 2 matrix. And remember I mentioned about determinant just now, so you can see the determinant plays a role here. So this is the determinant of M, and if you find that this determinant of M equals 0, then you have a difficulty. You get 1 over 0. Okay, so that's why it's important for your matrix M to have an inverse. You need your determinant of M not to be equal to 0. Okay, what precisely would be the inverse of M? Well, for the case of 2 by 2 matrix, it will be given by that, and one can check that this is related to something that we already seen before. It's actually your cofactors. Okay, your cofactors, remember what it is. You sort of remove the say ij ith row and j column to get your minor, and then you use the what you call the sign minor thing. Okay, so we go back to the things that we already learned before. So you can actually see for each of the elements M11, M12, M21, M22, you calculate your cofactors. It gives you these numbers, and these numbers are the one actually appearing on this part. Okay. In fact, you have to arrange it in such a way that cofactors over here, okay, cofactors over here is supposed to be arranged in this way. But instead, okay, so this will be equals to C over here. But instead, what you have is the C transpose. So you get C11, C21, C12, C22. You look at that, C11 is D, and then C12 is minus C. Minus C appears here. So it's not here, it's here, but not here. Okay? So in other words, you have to transpose this in order for it to be in the right position, and essentially that gives you the M inverse that you know. And this is for the case, the special case of 2 by 2 matrix. But nothing now limits you to 2 by 2 cases, because you know all these cofactors. You can actually generalize it for the case of n by n matrix. Okay, so one can revisit some example that we have done before. Here's a 3 by 3 matrix. Try to calculate using this cofactor thing. Okay, so you have your first you need to calculate your determinant of M. Okay, so in this case your determinant of M is not 0, so that means you can actually invert this matrix M. Okay, and then you calculate your cofactor matrix, and it becomes that. Okay, please again do the calculations yourself to convince your own self that this thing works. And then you multiply with 1 over the determinant and take the cofactor matrix and transpose it in this way. Okay, then essentially you have that to be your we claim it to be the M inverse. Okay, So in these types of calculations, it's useful to recheck. Okay, so we have to make sure, okay, if this is really M inverse, then one can essentially just multiply these two matrices together. So here's the M inverse here. Okay, here's M. See if it multiplies to give you the identity matrix. Okay, this will be slightly hard work because essentially the thing that you have all this determinant process makes it a bit hard to compute things, but in any case you need to recheck it at times because you want to make sure that your answer is right. Okay, so finally you get this to be your identity matrix. Okay, over here again, the theory behind this, why does this thing works, essentially is again from the properties of determinants. Okay, so here is the Laplace expansion of your determinant of M. Okay, this one is actually expanded about rho I. Okay, you see that here is the sum over K. Okay, this is K, this is K summed there, and the expansion is over this rho I. Okay. Now suppose for some reason you have your I and j rho of M to be the same, then you know the answer to this equation. The answer to this equation, if I and j rows are the same here, then your determinant has to be equal to 0. Okay? Or I can rewrite the above equation. Okay? Here I'm using I here, I'm using I here, using j here, using j here. Since I and j are the same, I can replace one of them by j. For example, over here, over here, let me write this carefully, and we retain the other I or I in this thing, we retain it still over here. Oops, no good at this step thing. Okay. So that retain, but we just replace the one over here by j. Okay, because the assumption here is to have rho I and rho j to be the same, and that gives you the answer determinant M equals 0. Okay, so now I rewrite your determinant M on the left hand side by the equation here, okay, which is that equation, okay, mjk cik. But if you look at this looks like a matrix, this looks like a matrix, but your the thing that being summed over here, your k, is not in the adjacent position. So if you want to make them adjacent so that it looks like a matrix multiplication, I have to flip the k over here to this the first index and get it to be transposed. Then this looks like matrix multiplication. Matrix multiplication. And we use the fact that this has to be equal to 0 when one rho I with a different rho j are the same. Okay, so here I and j are not the same number. Okay, I and j are different rows, but they apparently have the same matrix entries. So the way we do this is to say that this is actually equal to 0 is to use a Kronecker delta. Okay. You can remember Kronecker delta. When I and j is not the same, this is actually goes to 0. Okay. When I and j are the same, that means I'm looking at row, say I, I'm comparing with row I itself, that will just give you determinant m. So I will have to be this to be equals to 1. Okay. So that tells you, okay, I have that equation now. And this delta ij, this delta ij over here can be thought of as the matrix elements of the identity matrix. So in a way, what we have done, we are rewriting this as a matrix equation. We should look in terms of matrices in this way. 1 over determinant, well, okay, I'm putting the determinant m on the other side. 1 over determinant m times m, which is this one, okay, times C transpose, okay, times C transpose here. This is that. And that has to be equals to delta ij, which is the identity matrix. Or if you rearrange this thing, okay, then I will be able to say that, okay, if something multiplies m, okay, so if I write this way, m times 1 over determinant m, which is a number now, times C transpose equals to identity. So this will have to be, since it gives you identity, this has to be m inverse. So in other words, that tells us m inverse is simply 1 over determinant m times C transpose. Okay, so that sort of gives you the theory behind it. Again, you are not needed to know this by heart, but it will help you understand things much clearly now, hopefully, that why all these formulas work. Okay, so your I always have this joke about with my colleagues, particularly Dr. Resha, Dr. Chan, who has done a little bit of theory. We tend to remember formulas in our high school days, or no, in earlier days, without really understanding why it works. Now you are supposed to be able to grow in a way so that you understand why a particular thing works. Okay, either in terms of mathematics or in terms of physics, you have to have that kind of mental capability now. Okay, so hopefully this will actually let you know why that thing works. Any particular question at this stage? Because I need to have some feedback. Is this okay for you, or some of the things is probably a bit blurry, and probably you need to digest a little bit more, which is understandable. In those days when I'm a student, I normally take time. So when I go for a lecture and then I go back, maybe a few days after that even, then I'll try to re-understand what the lecturer is actually saying. Any questions before we move on? Because we need to move on. After this will be slightly a different topic. Are you still there? Okay, great. So we are still inside that same chapter now, but we need to understand more about matrices, but a special kind of matrices. So one of the things that we want to understand is how matrices help you understand rotations. Okay, so one of the things that we always do is to rotate a coordinate system. Okay, so let me go to the picture here first. I have it. So you have this point being rotated in some way, so you can actually see some kind of rotation here. Okay, go to this particular point. Okay, so then you might say, what would be the transformation law in that particular case? Well, let's say you have this kind of thing, x equals to ax plus by, x, capital X here is the coordinates of this new point after rotation, and it's given by these equations over here. And then you can see, okay, this again looks like a matrix equation, so I can write this x and y as a column matrix over here, and then your a and b and c and d are matrix elements here, and then your x, y here, your original variables in a column. Okay, so this is what we call an active rotation. What we do essentially to take a particular point, rotate it to get to another point. Okay, so this is active rotation. There is another way of doing this rotation ideas. Is instead of transforming a point to a different point, you look at one single point. For example, over here, you look at one single point here in the context of two different coordinate systems. So the ordinary coordinate system is this one, x and y here. Okay, so that will give you, say, the vector, the position vector r. Okay, r is your xy here. But if I were to have your axis of these coordinates being rotated instead, okay, and the point is still the same, okay, this vector is now a different vector. Well, I mean, it's the same vector in when you go back to the same coordinate system, but it's actually a different vector r dash. And this r dash, according to this rotated coordinate system, is given by x dash, y dash. So over here, we have a different description of rotation called the passive rotation. Why is it passive? Because your points does not change, but your axis changes. Okay, so you're just having two different perspectives of the same point. Okay. So in that particular context, you can have the same kind of matrix equation again. You have x dash, y dash corresponding to this new coordinate axis. Okay, so you cannot see my cursor, and I probably have to highlight where I'm pointing, and then that will give you the coordinates there, and the equation that defines the rotation, that's the coefficients there, and then this will be the original coordinate vector. Now, in this kind of rotation, what can you understand? What is the thing that doesn't change? Particularly with respect to this vector r here and vector r dash. What doesn't change? The answer is just below. You can just read it. What doesn't change? I'm comparing these two different vectors, r, which is now given in terms of x and y here, okay, and r dash given in terms of x dash, y dash. But what properties of this vector actually doesn't change? the length of the vector. That's right, because you can see underneath, right? Oh no, you understand it. So here is the length of the vector. The length of the vector in terms of the new coordinate system is given by x dash squared plus y dash squared. This is actually the length squared. Okay. Length. How do you spell length? L-E-N. Okay. This is the length squared of in terms of x dash or y dash, and this is the length squared of the in terms of the old coordinates. So effectively, no, if the length squared is the same, that means the length is the same. Okay. And a transformation that does this, okay, remember that these are actually different coordinate systems. A transformation that does keep this length invariant is called an orthogonal transformation. Okay. And this orthogonal transformation has this property of following. If we take the matrix M that gives you, the say R dash, sorry, I should be doing the other way, sorry. You take the matrix M that turns your R into R dash, okay? And this is essentially a rotation kind of, well, we're going to call it rotational matrix. But one of the properties that it's going to have is that it has this M, if we take the transpose, is just equals to M inverse. Now, how can you actually see this? Well, the point is just to write down the transformation law. Okay, here's your length squared in terms of x dash and y dash squared. Okay, but now I'm writing this in terms of your equation there. Okay, and expand that square. And essentially what we need in this particular case, it must be equals to the original length squared. So what does that mean? If I consider this what I call equation here, or this expression in the second line, okay, and I compare with the third line over here, what do I need? I need a squared plus c squared equals to 1, so that I get x squared here. B squared plus d squared has to be equals to 1, so I get y squared here. But I need AB plus CD to be equal to 0. Okay. So then that kind of transformation will actually preserve the length. This will be equal. Okay. So I need a matrix A, B, C, D such that this actually happens. These properties happen. And this can be done by multiplying M with M transpose. So here's M, here's M transpose. And when you multiply that, what do you get? Here, your A squared plus C squared. This one, your B squared plus D squared. This one, okay? And then your AB plus CD will appear on the off-diagonal thing. Since A squared plus C squared has to be equal to 1 according to this preservation of length here, and B squared plus D squared equals to 1. No, you cannot see my cursor, I have to mark it. Okay. And the off diagonal is actually 0. It's coming from this equation. So what does that tell us? Okay, M transpose times M must be equals to the identity matrix. This is the identity matrix. Or in other words, your M transpose has to be equals to the M inverse. That's great. So we have learned something new in some sense, that okay, if you have this M transpose times M equals to I, it corresponds to some kind of coordinate axis rotation. Can you make it this a little bit more quantitative in some sense? No, these are just relationships. Well, if you look at the relationships of your A and C and B and D, it must be equals to 1 when you sum the squares. It reminds you of a thing that we know from a trigonometric identity, which is cos squared plus sine squared equals to 1. So all you need to be able is to identify, okay, what is A, what is C, what is B, what is D. Okay, and the active rotation that we have before, okay, I'm going back to the first picture. Okay, the first picture, the active rotation, the rotation matrix will look like this. Given that your A, B, and C and D will be one of this cos and sine thing. Okay, so this is for active rotation. But there's another picture that we are supposed to know, correspond to the coordinate axis being rotated. So the coordinate axis being rotated, you have your minus sine theta instead of over here. You have your minus sine theta over here. This will be your passive rotation. So let me know if you have seen rotation matrix before. Have you seen rotation matrix before this? So this is the first time that you see this matrix. Okay, never mind. So then essentially this kind of it gives you a different sense over here. The minus sine theta here is coming from if you think of what is active and what is passive, it's actually related to one another. Okay, so one is rotating in certain direction, the other is rotating in another direction. Okay, so and that essentially tells us, okay, because one is rotating in the opposite direction, and the odd function here is given by sine. You have already done the trigonometric function power series. This is an odd function, meaning what? Sine minus theta equals to minus sine theta, and your cos theta is an even function, so cos minus theta is cos theta. Okay, and you can see the relationship now. Okay, one is turning your rotation in the negative direction. Okay, like before, this is the one that we have seen before. This rotates there, so this is negative theta in some sense, while the other one is with respect to the axis is rotated in this way, so this is theta. Okay, okay, I hope that clears things up. Usually people could get confused, okay, which matrix you want to use as a rotation. Okay, so you have to ask, okay, which one correspond to active rotation and which one correspond to passive rotation. Okay, so now we have seen this is the property of the rotation of coordinates. Okay, one needs to be able to see different properties of this matrix M here. Okay, so you know that rotation matrix must obey this. Okay, but if we just have this, is it enough to say that this is a rotation? Well, one of the things that we can actually try to do, this is a matrix equation. So one can actually take the determinant of this whole equation, take the determinant of this, that must be equals to the determinant of that. This one over here is thinking of really is an identity matrix. Okay, this is actually identity. And the determinant of identity matrix is actually equals to 1. Oh, by the way, okay, sometimes this happens in books. People get lazy to differentiate between identity and 1. Okay, so sometimes they write this. Okay, they write this, and it's supposed to be a matrix equation. Then you you understand it by the context that this one is not really a matrix, but in this context, you have to understand this as a matrix identity. Okay, so please be aware of those kind of laziness of mathematicians or physicists inside their books. Okay, they tend to get no they understand it, but they just know, okay, I know that it's going to get no, your identity is behaving like 1, for example. Okay, so here your determinant of identity, you remember what is identity, 1001, take the determinant of that is just equals to 1. Okay, and this is the essentially your your right hand side. Okay, so on your left hand side you have your determinant of M transpose M, and one of the properties that we know, if you take the multiplication of two matrices, determinant of AB equals to determinant of A times determinant of B. Okay, so in other words, we have determinant of M transpose multiplied by determinant of M. But M transpose is just interchanging between row and columns. And if we interchange row and columns, it will give you the same determinant. So in other words, this gives you determinant M squared. I'll finish in a minute. So if you look at this equation, so here's a number square equals to 1. There are two different solutions, plus or minus 1. So which corresponds to the rotation? The one that corresponds to the rotation is plus 1. Okay, so we shall continue from this point onwards in the next lecture. So let me just take the attendance for today. Okay, and that's probably it for today. So thank you, everyone. So see you hopefully next week. Thank you. Okay, bye.